All right, welcome everybody. Today we're going to talk about lesson number 27. This is section 2.7, which is all about nonlinear inequalities, and we're going to focus specifically on polynomial inequalities. Just as a reminder, in this unit, chapter 2.1 to 2.5, that was all about the polynomials, the nice, smooth, continuous curves. That's the kind of inequality we're going to focus on today. And then section 2.6 was all about rational functions. Those are the graphs with the discontinuities and the asymptotes. We're going to talk about those kinds of inequalities tomorrow. So before we talk about polynomial inequalities, let's talk about polynomial equations, and let's start with a really easy one. If I was going to ask you to solve this equation for x for the values that made it equal to 0, you would more than likely start by trying to factor it, x and x. Factors of -3 that add up to be -2, that would be x minus 3 and x plus 1. That would give you answers of 3 and -1. And if this was a polynomial equation, then those would be your only two answers, and you would call it a day. What we're going to talk about today is, well, what if instead of being equal to 0, what if it was that same polynomial, but this time less than 0? So just so you know, the first thing you would do is you would, again, start by factoring, same way. You would solve for what values made the inequality equal to 0. So you would, again, find the values of 3 and -1. But instead of those being your solutions, those are going to be what we call the critical values. And that's a very important vocab word in terms of calculus. Remember, as the year progresses, everything we do is going to be kind of having an eye on next year and what we're going to need for calculus. So again, if you're solving a polynomial inequality, then those values of x that give you 0 are called the critical values. And we're going to talk a little more about those on the next slide. So first, defining critical values. Critical values are the only values of x, and please be aware that they're only x's, where a polynomial can change its sign. That means from positive to negative or from negative to positive. Keep in mind that if you're talking about changing your sign, that means that these inequalities have to be in relation to 0, because that's the only location where you would change your sign from positive to negative or negative to positive. After you find the critical values, you're going to use them to create something called test intervals. And the reason why that's important is because in calculus, you're going to use these test intervals for something called the first derivative test and something called the second derivative test. So now that we're kind of hearing and using the word critical values, let's go ahead and kind of put the whole thing together. So going back to my inequality here. So again, I factored it. I solved for those x's. I realized that those are the critical values. And now here's what I'm going to do. I am going to set up a number line using my critical values. So set up a number line. You're going to draw a tick mark at each of those critical values in order from the smallest to the largest. You are going to use the factored form of the inequality, and you are going to test. You are going to test some value that's less than -1, some value between -1 and 3, and some value greater than 3. So those are your intervals. The fact that you're going to choose a representative sample from each of them is why those are called your test intervals. So let's go ahead and choose what I consider to be the easiest one. I'm going to choose something between -1 and 3. I'm going to choose 0. So if I take my 0 and if I plug it in for all the x's in my factored form, I'm going to get a -3 times a +1. Here's the thing. I don't actually even care that that is equal to -3. What I really care about is that answer positive or negative? Certainly you can see that it's negative. The fact that I got a negative for 0 means that any value that I choose between -1 and 3 is going to be a negative. So I'm going to go ahead and put a negative for that particular interval. Then you have to choose a value of x that is greater than 3. Choose anything you want. Sometimes, in my opinions, bigger is better. Yes, you can choose 4, but personally, I'm going to choose 10. If I choose 10, I'm going to get a +7 times a +11. Again, I don't even care what that answer actually is equal to. All I care about is that it is clearly a positive number. Choose something less than -1. Again, I choose to always go big, so I'm going to choose -10. If I choose -10, I'm going to get a negative times a negative, which of course yields a positive, which means that I am going to get a positive over here on the left-hand side as well. After you have chosen one value from each of the test intervals, you now have to interpret it in terms of what the problem is asking. So this is asking for all the values of x, all the locations where the graph is less than 0 only. So that means you are not going to actually include the critical values. You're not actually going to include -1, and you're not actually going to include 3, but you are going to include everything that's in an interval less than 0, which means everything between -1 and 3, which means that your answer to this inequality would be parentheses, -1 to 3 parentheses, which means if you picked any value, any integer, any decimal between -1 and 3, not including them, that is always going to turn the equation into something, or the inequality into something that is less than 0. So take a look at it. You would factor it, again, find the critical values, set up the test intervals, and then interpret it in the context of the problem. We did all that hard work, so we're going to take it and then kind of extend upon it. So here, again, the critical values. Now let's go ahead and take a look at that same inequality, but now notice that I'm asking you to interpret it in different ways. So just so you're aware, this would be the same factorization and the same number line. So this is still going to be x minus 3 times x plus 1. And you're still going to get that same number line where these are all positive, these are all negative, and these are all positive. So we're going to take that same polynomial, but now we're going to interpret it in terms of the 4 possibilities. So we already answered the question, where is it less than 0? Now we want to answer the question, where is it less than or equal to 0? So where is it less than or equal to 0 means where is it negative, but also include the critical values. So the answer to this polynomial inequality is going to be bracket -1 to 3 bracket. Then let's say that we want to answer the question, where is this polynomial strictly greater than 0? So if we want to know where this polynomial is greater than 0, we want the positive locations, but we don't actually want the critical values because it's not equal to 0. So how are we going to say that as a solution? Well, we're going to say all the values from -infinity to -1, and then all the values from 3 to infinity. Finally, last but not least, what if we now want to solve the inequality greater than or equal to 0? Well, again, we want all the positive locations, but we also want the critical values, which means we're going to want -infinity to -1, and then 3 to infinity with my brackets. So again, the same problem kind of showing you with 4 different interpretations. No matter what the problem is asking you, though, you're going to factor it. You're going to find the critical values. You're going to set up a number line. You're going to use the test intervals to find positives and negatives, and then you're going to answer the question in the context of whatever is being asked. So obviously, let's try some more. Before we do that, just a note, when you are trying to test the values, it is generally much easier to do it in factored form as opposed to standard form, although you should get the answer the same either way. Please note that if the polynomial is not factorable, which will happen from time to time, if it's a quadratic, you're going to use the quadratic formula. If it's something degree 3 or bigger, you'll of course have to use the rational root theorem. So please don't get it twisted. Don't think just because it's not factorable, it's not solvable. It just means you have to do a little bit extra work. It doesn't matter if your critical value is a decimal or a radical because you're choosing values in between and to the left and right of them. So it really doesn't matter what that critical value is. Let's go ahead and try the following. So the first thing you notice, hopefully, is the fact that greater than -48 doesn't mean anything. If you're trying to talk about positivity and negativity, that is only going to mean anything in the context of 0. So start by putting everything on the same side. This is a cubic of 4 terms, which means I'm going to try to group it. So I'm going to try to take the GCF out of each pair. From the first pair would be x squared, leaving me with 2x minus 3. From the second 2, when in doubt, take the negative out, and I can take out a 16. So that's going to give me a positive 2x minus 3. The fact that I got that repeat factor is actually really good. So that's 2x minus 3. And then x squared minus 16, that of course will factor again as x plus 4, x minus 4. And this is going to be greater than 0. So once I have it factored as much as I can, I am going to solve for my x's, 3 over 2, negative 4, and 4. Again, those are what we call the critical values. So I'm going to go ahead and set up a number line. I am going to take each of the critical values and list them in order from the smallest to the largest. So negative 4, 1.5, and positive 4. I now have to choose a test value in each of those 4 intervals. I am going to determine positivity and negativity, and then ultimately give my final answer. So again, when I do my test values, I'm going to use factor form, which generally is easier. So I'm going to start by choosing something in the interval that is greater than 4. So again, I usually like to choose 10 as my value. It doesn't matter. You could pick 5 or 6 or 7 or 7.27. Doesn't matter. You'll kind of find something that works for you. I'm going to pick 10. So if I then go and look at each of these intervals, I'm going to get a positive times a positive times a positive, which means that I'm ultimately going to get a positive. Again, I don't even care what the value is. You can find it if you want, but really all we care about is positivity and negativity. Something between 1.5 and 4, I'm going to choose 2. If I choose 2, I'm going to get a 4 minus 3, which is a positive, times a positive, times a negative. That is going to give me a negative. So negative here. If I choose something between negative 4 and 3 halves, I'm going to pick 0. Always try to pick 0 where possible. That is going to give you a negative times a positive times a negative. Notice that that should yield a positive. And finally, something less than negative 4, I'm going to choose negative 10. So that's going to give me a negative times a negative times a negative. A triple negative is going to be a negative, so I'm going to get a negative here. Now that I have all of my signage, please just make sure that you actually give me the answer. You are trying to solve the problem in the context of being greater than 0. So if you're talking about being greater than 0, you want the places where the pluses are, and you don't actually want to include the critical values because there's no equal to. So you would say that the answer is from negative 4 to 3 halves, or 1.5, and then from 4 to infinity. And again, you're going to just make sure that you're using parentheses because of the fact that there is no equal to. So hopefully the concept itself makes sense. It's really just a matter of how good of a factorer you are and how good of a tester you are. Let's go ahead and then for a second just kind of talk about some what I would call unusual solution sets. So it's just something that you want to be mindful of when you get a slightly different looking answer. So consider the equation x squared plus 2x plus 4. Just so you're aware, it is not factorable. If you were to use the quadratic formula, you would actually get imaginary numbers. Basically, what that means is that that quadratic is always positive. If you were to graph it, it would be all above the x-axis. So the fact that this is always positive, what that means is that there are no critical values. There are no values of x that make it equal to 0. So if there are no critical values, you can't actually set up a number line, but you still can answer the question. So if we deduce that this quadratic is always positive, if the question is where is this greater than 0, the answer of where this is greater than 0 is everywhere, which would be all real numbers. If the question is where is this less than 0, if the question is where is this less than 0, then the answer is nowhere, and you would say no solution. So again, as you do the homework tonight, if you get something that is not factorable, again, that doesn't necessarily mean that there is no solution. It means there's no critical values, but you still have to be able to interpret it in the context. So that's the first kind of 2 examples of how you might get what's called an unusual solution set. Let's take a look at another example. Let's say you had x squared plus 2x plus 1 equals 0. If you were to factor this, you would get x plus 1 squared, which would give you a critical value of negative 1. If you were to set up your number line of negative 1, Because of the fact that it's x plus 1 squared, no matter what you plug in, you're always going to get back positives. So if you get back positives on both sides, how would that help you answer the question of where is the graph less than or equal to 0? If you want to know where the graph is less than or equal to 0, well, it's never less than 0, but it is equal to 0 only at one location, and that's only at -1. So that's the only answer to this question is -1 only. If you're trying to use this and answer the question of where is this greater than 0, well, this polynomial inequality is greater than 0 everywhere except -1, because that's where it's actually equal to. So you would say that the answer was -infinity to -1, and then -1 to infinity. So just make sure that you are interpreting each of these problems, in the context that they're being asked. Let's go ahead and look at another one. So again, not a terribly difficult one. Really, the only reason why I even brought this one up was because of the fact that you can either move everything to the right side, or perhaps you would want to divide everything by a -1. And I want to remind you that if you multiply or divide by a negative, you of course have to reverse the inequality. We've known that since our Algebra 1 days, but it becomes more important than ever here. So if you're going to multiply or divide by a negative, please make sure you reverse the inequality. So this is going to give me a positive x squared. This is going to give me a negative 2x, and then a -3. And then when I reverse the inequality, I'm going to get greater than or equal to 0. And then again, this is going to be one of the problems that we already solved. So I just really want to make sure that you remember to do that. And I don't know that if I meant it to be the same one because we already did this problem. So I guess I really just wanted to remind you to flip the inequality. So no need to do the problem twice. Finally, in terms of the inequalities, consider these two. So these have already been factored for you, and I just want to talk of them in terms of how you would interpret them. So the critical values would be -2 and +1. If you were going to, again, test your intervals, let's say that you were choosing something greater than 1, like 10. If you were choosing 10, you would get a positive times a positive, which would yield a positive. If you were talking about something between -2 and 1, again, I would most likely choose 0. If you did that, you're going to get a positive times a positive, which is positive. And if you are going to choose something less than -2, like -10, you are going to get a positive times a negative, which is a negative. So notice here that you do have a change at -2, but you don't have a change at 1. So again, this is really just more about how do you interpret this. So if you're talking about using it to interpret where is it greater than or equal to 0, if you're talking about where is it greater than or equal to 0, you're talking about anywhere that it's positive, including each of these critical values. So the answer to this question would start at -2, including it, and then you could actually just go all the way to infinity because you're including all the test intervals, including 1. How would you interpret that in the context of just greater than 0? Well, if you're saying just greater than 0, it means you want to include the positive intervals, but you don't want to include the critical values. So you're still going to start at -2, but you're going to have to do so with the parentheses. You're going to have to take a break at 1 because that value is not actually included, and then you're going to have to go off to infinity. So I think that the concept of how you solve a polynomial inequality is relatively straightforward. The last thing I want to talk about is how does it relate to domain? So first of all, just a quick review of domain. Remember, of course, you can't have a 0 in denominators, and you can't have the square root of a negative. So in something like the first one, the only value of x you could not have would be 2. So you would say that the domain was -infinity to 2, and then 2 to infinity. For the one in the middle, you would say that whatever was under the radical would have to be greater than or equal to 0. which means that x would have to be greater than or equal to negative 5, which means that the domain would be bracket negative 5 to infinity. Kind of putting those two things together, if you had the square root of x minus 6 in the denominator, not only can you not actually have 6, but you also can't have anything that would make a negative. So you would actually say that x minus 6 has to just be greater than 0, which means that x would be greater than 6, which means that the domain would be parentheses 6 to infinity. So what does that have to do with what we were talking about? Well, our final example of the day, let's say you want to find the domain of the square root of 216 minus 6x squared. So we've seen these a couple of times, and we've actually seen this idea of a test interval, but certainly not lately. Here's what the question is actually asking. If you're being asked for the domain of the following, what you are actually trying to do is you are trying to solve the inequality 216 minus 6x squared is greater than or equal to 0. You need whatever is under the radical to be greater than or equal to 0. So you're going to go ahead and try to do that the same way you would using what we just set up. So you're going to go ahead and start by factoring under the radical. You can take out a greatest common factor, which is 6. That's actually going to give you 36 minus x squared. That's going to factor again as the difference of squares, so 6 plus x and 6 minus x. Notice that even though you're technically talking about something under the radical, you're only solving the equation without the radical. So really what you're talking about is 6 times 6 minus x times 6 plus x. Sorry, should be one of each. So you're going to consider, where is that equal to 0? 6 does not ever equal 0. So your two critical values are going to be negative 6 and 6. You're going to set up a number line using those critical values of negative 6 and 6. You are then going to test in factored form without the radical, because again, this is what we're actually solving. If we're talking about domain, that's the equation that we care about. So as you test, please note that the 6 doesn't matter because 6 is always positive, so we don't even have to consider it. So as we go to test, let's say that we're testing something like 10. If we test 10 in these parentheses right here, we are going to get a positive times a positive. We're going to get a negative. So 6 minus 10 is a negative times a positive. That's going to yield a negative. So that negative is going to go right here. Between negative 6 and 6, I'm going to choose 0. So that's going to give me a positive times a positive, which is positive. Something less than negative 6, I'm going to pick negative 10. So 6 minus negative 10, that's actually going to be a positive. 6 plus negative 10, that's actually going to be a negative. So I'm going to get another negative here. So I'm looking to answer the question, where is this greater than or equal to 0? So greater than or equal to 0 means wherever there's an addition, including the critical values. So the answer to this inequality is actually the domain of f of x, which would be everything from negative 6 to 6, including those values. So again, you can use this idea of critical values and test intervals to help you find the domain anytime you have the square root of a polynomial that is not linear. So we'll talk more about that later in the week. For now, homework number 27. This is in section 2.7. Each of these are just polynomial inequalities. So if you follow the process of today of factoring, finding the critical values, and testing, you should be more than fine. So thanks very much for tuning in, guys, and we will catch you next time.